Okay. Hello, Professor. Whenever you want, you can start.
Okay. Okay, you should be able to see the screen, yes. Here we go. Okay, so nice to meet you all. My name is Emanuele Della Valle, and I've been working on the topic that you see here for something like 14 years now. And yeah, the presentation is far from the one that you have just seen from Matteo. It's really more an advertisement of the topic than a list of theses. String reasoning was meant to be an approach to blend artificial intelligence and string reasoning, and I will sort of explain you what it is about in this short presentation. First of all, let's agree on a few basics, right? So data engineering and data science definitely contain volume. We know that there are techniques that definitely scale to huge sizes. And in this setting of data velocity, they also are progressing up to the point that is really possible to attain velocity either in the millisecond scale, if that what matters is latency, and in, let's say, the throughputs, if what matters is to maximize the amount of data that you can process in the unit of time. What is still impossible is somehow to tame them simultaneously. So there is a sort of grid wall in the area where you want to process petabyte in minutes. And so the limit today is a kind of trade-off between how fast you want to go and how many data you want to process. Keep this in mind, I will comment on it just in a few slides. And indeed, you can tame variety using artificial intelligence. And here, just to pitch you what I have in mind when I think to taming variety, I mean that given an image, and maybe soon also giving a movie, what you can do is have a machine understand the content in terms of a knowledge graph that represents what the machine sees. Now, the bad news is that as soon as you bring variety in, then the problem of this trade-off gets worse, and easily the problem gets harder and harder the more the variety comes in place. However, there are a number of users that somehow would like to go for all these at once. And just to give you an example, I've been working a few years ago back on a project with the 𝗙𝗏𝗏𝗏 company in Norway, in which the problem was really amazing because they have hundreds of thousands of sensors from tens of different producers, so high heterogeneous, that were streaming tens of thousands of observations per second. And I mean, many of these sensors were not even correctly streaming information because they were not operating within the ranges. And they have to somehow answer in a very short time to extremely complex questions like, shall I keep drilling in this moment when I see vibrations that are correlated to historical time series in which we had problems before, right? And the problem is very important because somehow you don't want one of these drills that are tens of kilometers away from the platform to get stuck, because basically you will cause a lot of money loss and potential ecological problems. Now, without staying more on this, the requirements for this kind of problems are a kind of conflicting, because what you have is, on the one hand, massive data sets. On the other hand, you have these data streams that keeps coming on you and they keep somehow arriving. They are heterogeneous, so there is the variety dimension. And then more interesting things come in, right? Many of these data are incomplete, and that can even be a veracity problem or a variety problem if you can fill them up, maybe by using artificial intelligence technique. And they are noisy, which it's again something that you simply cannot forget. And people want to provide the answer in a short time, where short normally doesn't mean millisecond, but it can mean that you have to provide an answer before the new information coming will make you change your mind about the correct answer. So what? Well, so in order to address these conflicting requirements, something like 14 years ago, we created this idea that indeed one can take string processing, which indeed is a pretty interesting way to build databases instead of having fixed data and dynamic queries. What you do is registering your queries, and then you observe the data through a given window. The data pass by, and you operate on this data while they pass by, generating a stream of answers. And that was, a good starting point, because if you compare string processing with the requirements, you realize that indeed they work for massive data, and of course they are meant to work for data streams. Many of these techniques are somehow robust to noise. They do reactive answer, but what they are missing is the ability to cope with a largely heterogeneous data set, and explicitly, and also with incomplete data that you may want to repair by using some kind of reasoning. And in that sense, the complementary part will be artificial intelligence, because it is definitely meant to work on this variety of data, heterogeneous data sets. And up to some point, it works with incomplete data, meaning that you can deduce what you don't know. But yeah, at a certain point, this thing stops to be so nice, and it is exactly when, at least back in those days, you get to data streams and to reactive answers. So the very first time we frame as a community the question, the research question, it was 2010, in which we wrote down this sentence, this question, into a paper. And basically we decided that stream reasoning basically answered to the question, is it possible to make sense in real time of multiple heterogeneous, gigantic, and of course noisy and incomplete data streams, in order to support the decision process of extremely large number of concurrent users. Now, just to make this a bit more concrete, I hope that you understood what the string processing is about. Let me give you a short example. Imagine that you have these strings of colored up boxes, and you have a window, in this case a logic window of 1 minute. The system that does string processing will be able to answer to query like, which are the top 4 most frequent colors in the last minute, or also to question like, is there a green box followed by blue box in the last minute, which of course there are many of them. Now, that's the basic technology, right? So what we did was, why don't we add here symbolic artificial intelligence? You have an ontology that captures the terminology that you use to describe a part of a word. And what you do is basically saying, why don't I use such an ontology together with a string processing in order to answer to questions like, which are the top 2 most frequent cool colors in the last minute? Meaning that there are no cool color, right? So if you look into the stream here, what you find is that simply the stream is made of colors, but cool colors have a definition. Red, violet, violet, blue, green, all of them are cool colors. Meaning that whenever somebody asks for such a question, what you can do is basically register all the equivalent questions and try to. Interestingly enough, another artificial intelligence that wants to speak. Okay, another example would be is very. Sorry for this. And is very primary cool. Okay. Is very primary cool color followed by a secondary warm one. And that will be another example in which, of course, there is no answer. You have to reason on top of the terminology in order to come up with, yes, there is a yellow box followed by a pink one. Well, apart from Alexa interrupting us and showing that these artificial intelligence are a kind of invasive, that was what we call deductive string reasoning, meaning that you have these models and you use the models to enrich string processing. Something else that I'm interested in is what one may call inductive string reasoning, in which what you want to do is instead of reasoning on symbols that comes from a model, you actually reason on top of data. You try to learn a model. And you may be aware that the big problem here is the so-called concept drift, because you have to cope with the problem that even if you have a model, the model may change over time and you may be unable to somehow use a model that you learned in the past because the error becomes big after something that is called the concept drift. One early attempt to work on this inductive string reasoning was done by, I mean, the problem is well known, but in terms of string reasoning, we did this a few years ago when we were building the very first deductive and inductive string reasoning. And that was a joint work with Siemens back in those days. And the idea was to be able to detect situations in which, because of something important, in this case, it was the Avatar movie, something that was considered a bad thing, being a 3D movie, suddenly became something like the most important feature for a movie to be, right? And in order to cope with the problem, we were using multiple windows of different sides in order to learn models that somehow can both capture the long-term trends and the short-term hype. And I only learned a few years after that indeed that was something other people were working on. And I particularly want to bring you this adaptive sliding window approach, in which you can estimate the best window in terms of the amount of data that you need in order to learn a good model. And I started to work with Professor Buffet a few years ago, and we are currently contributing both to MOA and scikit-learn multiflow, that are the two main libraries that somehow represent the state of the art of streaming machine learning. And the idea basically is to detect these drifts and learn new models when the drift happen. And here just few algorithms that come from the state of the art that you may want to explore if you go in this direction. So what? Well, the idea is that it would be nice to combine these two and build a generic system, not just something built on purpose for social media analysis as we did a few years ago. And that probably will do something like this. On the one hand, you still have a deductive string reasoning approach, but on the other hand, instead of having an ontology that is manually developed, you have an ontology that is continually learned from data, and something that captures the real semantics instead of some expert-driven semantics. And as a result, for instance, if the colored up set of words that you see here on the right would be an ontology of words connected to the color, just sticking to this easy example that I was doing before, you may start asking things like, which are the most frequent sentiments in the last minute? And then here you see there are the words connected to the sentiment. You can come up with saying harmony, because that is the combination of the color down into the stream. Or you may ask, is there an impulsive irritating colored box followed by an happy one? And that again will turn out to be a very complex query to write, but that doesn't matter, because the point is that you can express it in an easy way. Then it will be a compiler that generates the code to answer such a query. Okay, so what? Well, this was a fantastic scientific travel. We wrote as a community an amount of papers, something like 1,800. I discovered it myself just a few minutes ago. I was just missing something like 300 papers published last year. And what we probably demonstrated is that indeed you can take the semantic web stack and extend it in order to represent heterogeneous data streams, continuous queries, and continuous reasoning tasks. Also, I think that the community proved that it is possible to somehow optimize continuous querying and continuous reasoning in order to provide reactive answers to many application use cases. Also, in the recent years, we started to develop models in which we are learning the ontologies in a continuous way from streaming machine learning techniques, and that to me is a good step towards this idea of creating inductive and deductive stream reasoners that sort of work out of the box. As an assessment towards the requirement, I think that we did a great job for data streams and reactive answers. That is really the main contribution of what was done in these 13 years by the community. I'm still not completely happy about the way we managed a heterogeneous data set. To me, they still look too homogeneous. I would really like to attack more semi-structured and unstructured data. Where I think there is a lot of space of improvement is scalability. And so these techniques tend normally to work in vertically scalable solutions. There is basically nothing seriously done in the space of horizontally scalable solutions. And also, yeah, I mean, we've been doing and we are still trying a lot in terms of incomplete and noisy data, but we are still lacking behind a lot. So far, going to the thesis, I think that this is just a list of ideas, and you can come and tell me what you are interested in case, and we can discuss. Definitely, there is the problem of understanding the semantics of stream processing languages. I mean, just the plain problem of processing data streams, and I think that is still a very important point in the space of the thesis. I would like, as I said before, to scale the data stream reasoning on Kafka, on Spark, on Flink, on anything else that looks like a scalable stream computing platform. Also, I would like to do more work in advancing inductive stream reasoning. I have a couple of theses running on streaming graph machine learning, on streaming anomaly detection, and other topics in this area. And also, yeah, I mean, probably the most challenging thing would be to build something that combines inductive and deductive stream reasoning. I'm also very open to applications. For instance, one of the things that I really would like to get done in a short term would be to take the picture that you saw before about the scene graph, the spatial temporal scene graph, and integrate it into a stream reasoner in order to do something that looks like this crazy movie from the past, if you remember, right? In which you have a machine that really try to solve a very complex problem, understanding the world in which it is, and coming up with a possible solution in a world that is full of noise, full of incomplete information, right? So a pretty common and complex thing that do not only, I mean, happen in movies. Thank you very much. I hope that this was interesting enough. If you have any question, I'm open to answer them. Otherwise, just contact me on one of the possible channels.
Thank you, Professor.
Thank
you
you
very much for the presentation. It was really interesting. I don't see any question on the chat, so maybe they will just contact you via email.
Thank you.
Okay, so
Yeah.
Thank you very much again. Now we will go to the next one, which is Professor Cremonesi.
Hello.
Okay, hello, Professor.
So today I'm here with one of my postdoc, 𝗙𝗬𝗟𝗢𝗪, who is I think he should be here online with me.
Yes, I am.
Okay. What I will do, I will give you a very quick overlook on the type of works we have in our lab, and later Maurizio will give you some practical examples. Is it okay, Maurizio? If I'm doing the opening presentation, is it okay? Okay. So just 1 second. I'm sharing my slides. Okay. So you should see my screen now.
Yes, we can.
Okay, perfect. Welcome everyone. This event is really a fantastic opportunity to explain the type of thesis that we have, to a large group of students. So it's a good way to save, our time and your time. So in our group, well, there is myself, Maurizio who is here, and we have also a number of PhD students. You see their name there. I hope I didn't forget anyone. And in our group, we mainly have thesis projects on the design and implementation of machine learning algorithms focused on recommender systems applications. All these, even if the topics could be quite different, all theses have a common structure. Okay, so I would like first of all to give you an overview of the structure of a thesis in our group. So the type of work we expect from you in case you take on one of our projects. Okay. So first of all, you as a student, you should understand the goal of the thesis. And later on, we are doing algorithmic research, and in algorithmic research, there is no, an absolute good or bad project. The quality of a project is always relative to other projects. Okay, so the goal of all our works are to be able to improve with respect to what other researchers have done on a similar topic. So once you understand the goal, the next step is for you to understand the state of the art, so the competitive solutions, and you need to understand how this competitive solution works. Okay, we call them the baselines. And as a next step, as we are doing again algorithmic research, we are not able to assess the quality of a project by using any mathematical proof. Okay, the only way to evaluate the quality of a project of an algorithm is by testing this algorithm on a number of real data sets. Okay, so the next step is to identify which are the data sets that we can use for the evaluation. Okay, different problems require different data sets, and you as a student, you have to pick up the proper data sets, or eventually to create them. Okay. Next step, and as you see, up to now, you have not yet implemented anything new. Okay. And the next step is to implement the baselines. Okay, because very often the competitive baselines are described at a high level, but there is no code available. Okay. Well, if the code of the baselines is available, you are lucky. Okay, but if not, you have to implement the baselines, and then finally, after all of this, you can start working on the novel approach. Okay, you start implementing your novel approach. You have to compare the novel approach with respect to the baseline. Quite sure, in the first implementation, your novel approach will work badly. So you have to improve your approach, and you have to iterate this, okay, until you are able to do better than the baselines, or until there is no more time, or until we think that this original idea was not so good at the very end. Okay? Because it happens in research that it is called research because we search something, but we are not sure we will be able to find something good. So this is the common structure for all thesis projects we have. And as for the topics, we have two big streams of topics. Okay, one stream is about, as I was saying, machine learning. Machine learning applied to recommender systems. Here is one example of a thesis project we had last year. Okay, or it could be probably 2 years ago. This one. So the goal here was to compare a number of deep learning techniques for recommender systems and to compare them against a number of other baselines in order to evaluate which of these baselines was the best one. Okay, so in this thesis, this thesis was unusual because the student was not asked to implement anything new. The student was asked to implement only baselines, which seems trivial, but is not. If you have to implement a deep learning technique, even if this technique has been described somewhere, it's not easy. Okay, and by the way, the results of this thesis have been, awarded with a best paper award at Rexis 2019. So we have a number of thesis projects on this type of topic, but we also have several students doing a thesis on this at the moment. Okay, so in the short term, so if you are looking for a thesis work and you want to start this thesis, in the next few weeks, as far as I know, then maybe later Maurizio will confirm or deny this, but we do not have open topics on this. Okay, because we have open topics, but we have also already have a lot of students working on this type of topics. Okay, there is a second family of projects we are working on, which are about the usage of quantum computing in order to solve machine learning projects. Okay, and of course, for most of the projects, we are focusing again on recommender systems applications. Okay, so this is again an example of a recent thesis. The student graduated, if I remember well, in December. Okay, here the goal was to use a quantum annealer to implement a portion of a machine learning recommender system. Okay, and the results were that it was possible to do the porting on this on the quantum annealer, and the new algorithm was 10 times, roughly speaking, faster than a conventional algorithm with also better accuracy. Okay, and we are submitting this work to 𝗒𝗫𝗎𝗓, which is an important conference. So this, to give you as I was saying, a brief overview. Now, I would like Maurizio to go deep into some of these topics. So I am letting the stage to Maurizio.
Thank you.
And I stop sharing.
Okay. Can you hear me?
Yep.
Okay, thank you. So yes, as Paolo Cremonesi said earlier, we have been working in reproducibility and evaluation of neural models. We have some articles with some works which have already been on the way for a little time, so we would like to close some of them before we start a few new ones. So if you are interested in these topics and you plan to start the thesis in a few months, we may have some topics available. For the moment, we instead would like to, we have a few other topics open in the field of applied quantum machine learning. Now, I will share my presentation and I will provide you in the beginning with just 2 very short slides of preliminaries so that we are all speaking the same language, because it's a vast topic. So you should see my screen. The people that are listed in this slide are a subgroup of our wider recommended system lab, which are those that are working more specifically on quantum machine learning topics. So if you choose a thesis with us, you will be supervised by a subgroup of those people. First of all, you may have heard about quantum computing and the potential of revolutionizing several fields of our science has been known at a theoretical level for decades, but developing a functional machine has been long elusive because there are several extremely difficult engineering challenges to overcome. Broadly speaking, there are 2 paradigms. The gate model, which in a sense is analogous to an electronic circuit because you have a state, a quantum state, on which transformations are applied using gates. And the adiabatic model, which leverages the adiabatic theorem, it's another type of approach that with the current technology is able to solve optimization problems. It is more, the 2 paradigms are in theory equivalent. The current implementations are not, but these are more technicalities. In practice, being able to solve optimization problems is not really a limitation, as a huge number of things that can be done currently, a huge number of things that you might want to do can be transformed in some way as optimization problems. Both of these are accessible on the cloud. IBM, Rigetti, IonQ all have machines that can be accessed freely if you are curious and want to play around with them. We are going to use the one from D-Wave, which is a quantum annealer and solves optimization problems. Why? 3 main reasons. The first one is that as of yet, it is the only one that has enough qubits to do small but realistic experiments. So you can do real experiments and solve realistic problems with it. It has around 5,000 qubits, so you can do some interesting stuff. It is programmable with traditional operations research tools. So if you're able to take your problem and transform it in a format, which is in the next slide, that should be familiar to any of you who attended the operation research course. It can be solved easily on a quantum machine. It doesn't require you to design an ad hoc solution with quantum gates. Also, it has a solution time in the range of milliseconds, with the annealing time being in the range of 20 microseconds. Of course, the machine is available on the cloud, so you have some internet time and queue time, but the solution is rather fast. So what is the general goal of the thesis? The idea is to take a certain problem and represent it as an optimization in the format of a quadratic unconstrained binary optimization problem. Essentially, a minimization problem which has binary variables and has a certain type of constraint. The constraint, cannot have constraints. If there are configurations you do not want, you represent them as penalties in the objective function. And the format is here below. So you see you have variables multiplied with a matrix Q, which is square. The goal is to map something in this formulation. And the problems in this format can be solved easily with classical tools like simulated annealing, for example. So you're not bounded to use a quantum machine alone. There is lots of options to experiment with classical systems if you want to prototype. Now, to some topics. The first one deals with the difficulties in representing user behavior when you have certain item features. For example, you have a book. What type of features do you have? You can use text extracted from it. You have a movie. Well, you can have metadata, say the genre, the authors, and such. But are these features really representing the user perception? If you compare the similarity of two items based on the way the users interact with them and based on the features they have in common, there are two possible scenarios, broadly speaking, that the items are similar but shouldn't because the users are not considering them as similar, in which case you have features that are redundant and you should remove them, or the items are not similar but should be because the users interact with them in a similar way. Missing features, well, you cannot create missing features, of course, but what you can do is you can deal with a specific subproblem, which is if you have a representation that is too fine-grained. The topics, the concepts are too specific. So what you can do is you can generalize. You can build a model which aggregates concepts you have in your data in such a way that items that were not similar before are now. So the goal of the thesis is to design a feature aggregation model that is able to generate new features as the union of existing ones to mimic the similarities you have based on the user behavior. Another option deals with a particular user interface. Now, I'm assuming you're familiar with Netflix and other types of movie-on-demand or music streaming services. And you will have noticed that when you open the page, you see a number of rows, thematically consistent. New movies, dramas, perhaps some recommended for you. So there are different rows which are called carousels. Each of them is built in a specific way. Now, if you want to select the optimal page layout, well, that's a difficult problem because you have interactions between the lines, between the rows. You don't want to replicate recommendations in multiple places because if you show the user the same thing multiple times, that is not beneficial, really. So you want to balance a number of correct recommendations you provide with a certain diversity. So you want to help the user explore. This is, again, a combinatorial problem. It is not very well studied in research, but there are a few papers, and all of them are from companies: Netflix, Amazon, Spotify, Deezer, and LinkedIn, I think. So it is a topic of a certain industrial interest. The goal is to develop a way of selecting the optimal carousels based on a set of available models, which may be dozens of different models built in different ways. To experiment with different heuristics to determine whether you want those models together or not, and extend an existing proof of concept that we have been developing recently to account for example, clusters of users. Different user groups may want different interfaces. Another option is the porting of widely used models such as matrix decomposition. Now, you may have encountered matrix factorization or decomposition techniques in a few occasions. They are widely used in a number of fields, including recommender systems. The general idea is that you take a certain matrix A and you decompose it as the product of two other matrices, lower dimensional ones. There are a number of ways in which you can do that. Each has different properties. But recently, it was shown in a theoretical paper that it is possible to solve a certain type of decomposition, non-negative matrix factorization, with a hybrid classical quantum algorithm, which means that a step of the decomposition can be done by representing the problem as a Kubo optimization problem, hence can be solved with a quantum annealer. The goal of the thesis is to study this result, implementing the algorithm and testing its accuracy on a set of cases, as well as its scalability. Then tested it into a recommender system scenario, adjusting the model if it is necessary. Extensions are possible depending on the amount of work this requires. For example, non-negative matrix factorization has a nice clustering property, so one could see if these properties still holds and if it can be exploited. I think it is the last one, yes. Another option is when you train a model, you make often a certain assumption, that is, you want your model to be able, based on the training data, to predict the training data. A model which is able to do this is referred to often as stable because it has learned so perfectly to represent the training data that doesn't change, doesn't predict something else. So it is in a point where it stays and it remains. If you have a certain matrix which contains the interaction data and a model which is S, a square matrix, you have this kind of equivalence. So the original data is equal to the data, the training data on which the prediction is applied. Maybe this is not so familiar if you have not followed the recommended system course, but it's just a matrix product. Problem. In the recommender systems, we observed very few of the interactions possible. Imagine yourself in front of Amazon, how many articles it has, millions probably. How many could you possibly buy in a year? A dozen, maybe, or 100 if you're a compulsive buyer. But the greatest majority of the possible combinations of users and items are empty. The goal of this thesis is to try to represent this type of formulation, not as the training data on which a model is applied, but rather as a combination of two components, the data you have observed and you have in your training data, and positive interactions which you have not observed, but they exist. This is a Boolean problem, so it fits nicely in the optimization problem. So given a model, what you want to do, you don't want to learn a model, but you want to learn which are the missing interactions that would make the model stable. This would open a new set of options for co-training operations, for example, in which you jointly train a collaborative model, and then you try to discover missing interactions. We had done a few studies on this a few years ago, and it seemed an interesting directions to pursue, but until now it was unpractical because it is an NP-complete problem, and we didn't have an efficient way to solve it. Now we have. So I was very rapid. I hope you got the idea. If you're interested in one of those topics, send us an email. I am the one who is managing these things more directly, so this is my email address. If you're curious, we can have a chat about these topics. In case you have questions, please. If not, I will leave the floor.
Okay, seems
they got shocked by the algorithmic complexity.
Yes, so there are no questions and no survivors.
Oh, sorry, just a small detail. In practice, we have, for the people that do thesis with us, weekly, bi-weekly meeting with one of the people that is supervising you. So if you are new with these technologies or you are facing issues, we have relatively short latency between the next discussion. So we will be supervised closely. The prerequisites. Well, you have to be somewhat familiar with operations research tool. You don't need to develop your own solver, but to have an eye for how a loss function is computed, some basic knowledge on how machine learning works and on how you can conduct experiments, and Python, of course, because most of these activities is done in Python. There are not high prerequisites. So you don't need to be a specialist in, I don't know, advanced physics or advanced mathematics. There are theses which take into account the type of studies you have made. So they are tailored for your knowledge.
Okay, so if there are no more questions.
Yeah, I think there are no questions anymore. So okay. Anyway, they have your email address, so they will be able to contact you whenever they want.
Okay. Thank you very much.
Okay. Thank you for the presentation. Okay, I think that we can close the event. So because there are no more professors. Okay, thank you to everyone who was attended this event. I remember you that there is another session tomorrow, and basically it is at the same time. So see you tomorrow. Bye.